On the big island of Hawaii, some of the heat that drives the Earth's dynamo finds its way to the surface.
All right, now I'm in.
For several years now, Mount Kilauea has been continuously erupting.
Well done.
Scientists from the U.S. Geological Survey need to sample the lava to keep an eye on the volcano.
It solidifies pretty fast, as you can see.
But geophysicist Mike Fuller is interested in the lava for another reason: what it tells him about the Earth's magnetic field. It all begins when the lava hits the sea.
You can see the lavas having moved down from the volcano up here, sometimes in tubes, mostly in tubes. Now we're beginning to see it come out and go into the water and form the very newest bit of the island chain of Hawaii. As this lava hits the seawater, of course, it really chills very, very fast. And a very wonderful thing happens. They actually trap in, they record the Earth's magnetic field.
As they solidify and cool, these volcanic rocks are preserving a record of today's magnetic field. But the volcanoes of Hawaii have been erupting on and off for millions of years, building up the islands. Every layer of lava contains a record of the magnetic field at the time of that eruption. So the Hawaiian archipelago is a hidden chronicle of the Earth's magnetism stretching back 5.5 million years. That record shows there have been many fluctuations in the field's strength, but it contains something else of great significance. When lava cools, as with pottery, magnetic regions form within it. Acting like microscopic compass needles, they record not only how strong the field is, but also in what direction it is pointing. Today, the Earth's magnetic field runs from south to north, which is why compass needles point toward the North Pole, and recent lava flows record a field pointing north. But 50 years ago, when scientists measured the magnetism trapped in older lava samples, they made a startling discovery. The microscopic magnets within the lava were all pointing south.
When we go back about 700,000 years, we find an incredible phenomenon. Suddenly, the rocks are magnetized backwards. Instead of them being magnetized to the north, like today's field, they're magnetized to the south.
It seemed that prior to 780,000 years ago, Hawaiian lava must have cooled within a global magnetic field that was running to the south and away from the north, exactly the reverse of today. The bizarre implication was that at some point, the entire global magnetic field had done a sudden 180-degree flip, completely reversing direction.
It was hard for people to accept. They did not like the idea of the field reversed. It took about 50 years to convince people of this. But eventually, that was established, and really by work on this island, because if you keep on going down, you would find that after about another couple of 100,000 years, then it changes again, and you see this sequence going on.
And as they examined samples from older and older lava, scientists found more and more reversals. On average, one every 200,000 years.
And so by the time people had done that, it was pretty obvious that the field did indeed reverse.
But if the field has reversed so often in the past, it must surely do so again in the future.
That the Earth's magnetic field reverses is an extraordinary phenomenon. But this reversal process is quite common. The last reversal was, 780,000 years ago. Before that, there was one about 200,000. Before that, again, actually less than 200. So in a sense, we are a bit overdue for a reversal.
So is this why the field is growing weaker today? Could it be getting ready to flip? Scientists needed to discover whether there was a link between changes in the strength of the magnetic field and changes in its direction.
It was a very intriguing problem, something that was screaming out for an answer, and computers were becoming powerful enough to actually solve a full set of equations that describe convection in the core of the Earth and how that motion generates a magnetic field.
In the 1990s, physicist Gary Glotzmeyer decided to embark on a very ambitious experiment. He put all the essential facts that scientists had learned about the Earth's molten core into a computer model, dozens of equations describing its dimensions, temperature, viscosity, and so forth. Then he let the model run to see how the magnetic field would evolve over hundreds of thousands of years of simulated time.
It's important to understand just how long these simulations take. Each time the computer solves the equations, it advances the whole solution one time step. And the time step is typically 10 days. And within 10 days, things don't change much, which means you have to do many, many solutions. You have to solve it millions of times, tens of millions of times, in order to be able to simulate hundreds of thousands of years, which is what we needed. One case may take 6 months of running on the fastest computers in the world. I was using supercomputers from the Department of Energy, from NASA, and the National Science Foundation, and no matter where I was, the first thing I do is make sure the computers didn't crash. So it was something I did every day, 7 days a week, for over 4 years. And I remember there was a period of time, I believe it was in the fall, and I was traveling to other universities and giving talks, and after a number of weeks I came back and decided, well, now I need to look at the details of the magnetic field, and realized that it was in the reverse polarity. It already had reverse. This is something I didn't expect. So then I looked at many snapshots during the time I was gone and realized that the field did indeed reverse spontaneously. This is the first time it happened. We were very anxious to write about it. It was really exciting.
And as the experiment continued, so did the reversals, every 100,000 years or so of simulated time. And crucially, each time the field reversed, the process began the same way.
What's interesting is whenever it has reversed its polarity, its direction, that happened when the magnetic intensity was very weak. So it was decreasing, decreasing. Finally, when it was the dipole part of the field was very weak, then the field reversed.
Here was the evidence that what we are seeing today, a loss of field strength, is indeed linked to the onset of reversals. What's more, Gary could see why reversals are heralded by a weakening field.
Now this movie will show part of a simulation that spans magnetic field reversal. What you see here, blue represents inward directed magnetic field, the gold represents outward directed magnetic field.
In Gary's model, reversals seem to start with the appearance of islands of blue in the gold, and vice versa. These are magnetic anomalies, regions of the core where the field is already flowing the wrong way. As they grow, these patches where the field is reversed start to cancel out the main field, making it weaker and more liable to flip.
You see, as the time goes on, the field becomes more and more complicated, and then you get an anomaly growing in the northern hemisphere where magnetic field now is going out. There's the reversal. Now the magnetic field is outward in the northern hemisphere and inward in the southern hemisphere.
So now the burning question is what's happening in Gary's model reflected in the real Earth?